Okay, we have one more lesson with limits, and that's limits where x goes to infinity. Let me write down the simple one here. There's the way you write it. And what you mean is simply, you're asking the question, what happens to this function, 1 over x, as the values of x get larger and larger and larger, become arbitrarily large in the positive direction? And it's easy enough to see the answer. Here's the graph of 1 over x for positive x's. And we see that as x gets larger and larger and larger, the value of 1 over x just gets closer and closer and closer to 0. Going back to, remember the idea of the limit, it says that basically no matter how small of a little interval you put around the limit, you'll eventually get there. Or you'll get there if in this case, if you go out far enough. So no matter how far out you go, or let me say it this way, no matter how small of an interval you put around this line, you will eventually get within that interval by going out far enough. So the basic idea is just that this thing gets arbitrarily close to 0. Maybe it hits 0, doesn't matter whether it does, but the point is the limit is 0. In fact, let's do this one just by contrast. Sine of x over x. Recall that as you go to 0, this limit is 1. We're not going to 0 now. We're going to infinity. So here's the way you can draw that graph again. Remember how you do it? This is the function 1 over x times the sine of x. So this is basically your amplitude. So you can graph 1 over x like that, and then you graph its negative like that, and then sine of x is going to bounce between these two. When sine of x happens to be 1, 1 times this value is going to be that value. When the sine of x is negative 1 times this value is going to be down here. If the sine of x is 0, you're going to be 0. And so it's going to bounce back and forth. Recall that we know that it approaches 1 as x approaches 0, so it's going to look something like this. To be honest, I can't remember exactly what it looks like, but it's going to do something like that, where this is pi, and this is 2 pi, and this is 3 pi, and this is 4 pi. Notice notice my pi's get closer and closer together. They shouldn't do that. So they should stay the same distance apart. But with the board being this short, I'll kind of cheat on that. The point is it goes back and forth and back and forth. And so this is another case where even though it crosses 0 an infinite number of times as you go, the point is it's just going to get closer and closer and closer to 0. You give me any little interval around 0 on the y-axis, and eventually this will stay within that little interval. And so this limit is again equal to 0. So you have that. Okay, let's look at some other ones. How about this? Okay, something like that. What happens to this as x goes to infinity, as you go out farther and farther? Well, here's the way I like to think about it. I put it in military terms. If you think of these as being maybe infantry soldiers, and these as being people with machine guns, and these as being people with tanks, soldiers with tanks, it really doesn't matter how many infantry people or people with machine guns you have. It's the tanks that are going to determine the victory, because they just overpower everything else here. And similarly, it's the x squared. As x gets big, it's going to be the x squared that really makes all of this stuff almost irrelevant. In fact, it makes it irrelevant, okay? This is what's important. And here's the way to see, in fact, I can just look at that and say that this function, as x gets really, really big, is going to approach 4/3. And the reason I know is I'm going to again divide by a special form of 1. 1 over x squared divided by 1 over x squared. This divided by this is just 1. So now I can take each of these and multiply it by the 1 over x squared. And when we do, what happens? 4x squared over x squared is 4. 5x over x squared is going to be 5 over x. And then 8 over x squared is just 8 over x squared. On the bottom, as you multiply the 1 over x squared through by everything, you're going to get 3 minus 7 over x plus 12 over x squared. And now it's more clear, if it wasn't here, that as x gets big, just like I showed in the previous problem, this thing here is going to go to 0. Because x is getting big, so that goes to 0. This goes to 0. This goes to 0. And this goes to 0. So all those things are irrelevant. And the key is that the highest powers here, the ratio is 4:3. So this thing is going to approach 4/3. So again, if you were to put this function into your calculator or into Decimus and just go out a ways, you'd see that the function would level off at 4/3. So there's that one. What happens if we change it slightly? Let's make this a 4x cubed up here. Okay? We're still going to multiply both the top and the bottom by this. The key is you multiply both the top and the bottom by the highest power of x on the bottom. So the highest power of x in the denominator is x squared, and so you divide both the top and the bottom by x squared. Okay, so you do that. We've done it before. Let's do it again. We're going to end up with 4x plus 5 over x plus 8 over x squared, all divided by 3 minus 7 over x plus 12 over x squared. And again, you see that these four things here all go to 0. They all go to 0 as x gets big. 3 just stays 3. But the 4x, as x gets big, that's going off to infinity. This thing keeps growing. This just stays at 3, and these all go to 0. So the whole thing is going to be going off to infinity. So you've got that right there. Okay? What happens if instead of having the cube there, you have the cube down here? How does that affect things? Okay? Well, now the highest power of x on the bottom is x cubed, so we're going to multiply both the top and the bottom by 1 over x cubed. So now the top becomes 4x squared over x cubed is going to be 4 over x plus 5 over x squared plus 8 over x cubed. And on the bottom, you're going to get 3 minus 7 over x squared plus 12 over x cubed. And what happens here? These 4 here all go to 0. 3 stays 3. And 4x also goes to 0. Aha, all of these things go to 0. So the whole numerator goes to 0. These things go to 0. You still have a 3 on the bottom. So you get 0 over 3, which is 0. So there's that one. So that's the idea. Do a few of these and you can start seeing your own patterns and relationships about what happens with various powers. One other one that's maybe important to do, just for the algebra involved, is one like this. Let's see, how about, let's say 15x there. And on the bottom, we're going to have 3x cubed plus 2. How about that? Okay? Well, the highest power of x on the bottom is x cubed. Okay, so we're going to divide both the top and the bottom by x cubed, or multiply by 1 over x cubed. So it looks like that. And so what happens? The bottom is easy. This is going to be 3 plus 2 over x cubed. The top, when you bring the 1 over x cubed into the radical, you have to square it. Let's think about that. If I have 4 here, let's make it 9, just to make it very clear. If you have 9, let's say 9 times 2. 9 times 2, and you bring the 9 out, you'd have to bring the 9 out as a 3, because the square root of 9 is 3, and so if you bring it outside of the radical, you bring it out as a 3. If you wanted to bring this back in, you'd have to square it, and so you're going to get 2 times 9 again. Okay, so whatever goes into the radical, you're going to have to square it in order to keep it the same. So here I have 1 over x cubed. When I square that, 1 over x cubed times 1 over x cubed is going to be 1 over x cubed times x cubed is x to the 3 plus 3 is x to the 6th. So that's going to be x to the 6th. When I bring that inside, I'm going to have 5x to the 6th divided by x to the 6th, which is just going to be 5. Here I'm going to get 8x cubed over x to the 6th, which is going to be 8 over x cubed. And here I'm going to get 15x over x to the 6th. X divided by x to the 6th, what's that? Here you have 1x, here you have 6 of them. So 1 goes away and you have x to the 5th. So it's going to be x to the 5th. Okay? So there you go. What happens? As x goes to infinity, goes to 0, 0, 0, you end up with square root of 5 over 3. Like that. So there you go. Okay? That leads me to one of my favorite problems. I give this one to every calculus class I ever teach. What about the limit of the square root of x squared plus x minus x? What's that thing approaching as x goes to infinity? I love this problem because you could convince yourself of 2 different answers. Some people say, well, it might be 0 because this is much more important than this. So if you just kind of get rid of that, then you have the square root of x squared, which is x. Here you have x. X minus x is 0. So maybe this is really insignificant and you get x minus x, which is 0. That's one possibility. The other way of thinking about it is, well, without this, this and this are the same. The square root of x squared is x, so x minus x is 0. So you have this left over. And this thing all by itself is getting bigger. As x gets big, you have the square root of a big number. So maybe this is going off to infinity. So you can convince yourself that the answer is going to infinity. You can also convince yourself that the answer is going to 0. So either of those are reasonable. Maybe it does something in between. So let's see what happens. Are you thinking about the way to approach this yet? Should be thinking conjugate. It's not guaranteed, but it's certainly something to try when you have some messy thing here involving a square root. There you go. I just multiplied by a fancy form of 1. This over this. So you multiply it out, and what happens? This times this just gives you the inside, x squared plus x. Then, because it's a conjugate, this times this, and this times this are exactly the same, except that one's negative and one's positive. So they cancel each other out. And then finally, you're left with negative x times x, which is negative x squared. So you have that on top. And you still have this on the bottom, in the denominator. Okay? Well, what can you do now? Obviously, this x squared and this x squared can be taken away. They cancel each other out, and you're left with this. So notice, here I have, as x goes to infinity, this is going to infinity, this is going to infinity, similar to those other problems. Which one wins? What happens here? Well, as before, we divide by the highest power of x on the top. On the bottom. What is the highest power of x here? You might be tempted to say x squared, but it's really not, because you're taking the square root of that. The square root of x squared is x. There's another x. So either one of those, x just all by itself, 1 over x, is the thing we want to multiply by. What happens? X divided by x is 1 on the top. I take this 1 over x and I bring it inside. Remember, when I bring it inside, I need to square it, so it's going to come in as a 1 over x squared. So here I'm going to get x squared over x squared. X squared over x squared is 1. And then I'm going to get x over x squared, which is 1 over x. And then finally I have x divided by x, which is a 1 out here. So there you go. Now as x goes to infinity, what happens? The top is 1. This goes to 0. So you have the square root of 1 plus 1 is 1 over 2, 1/2. Very cool. So this limit here goes to 1/2. Not at all what I would have guessed. I would have guessed either one of these two extremes, 0 or infinity. Turns out it compromises and goes somewhere in between. And again, if you want to, just take a big number, put it in here, square it, add it, take the square root of it, subtract the number, and you should end up with something pretty big, pretty close to 1/2. So there's the end of limits. In the next lesson, we're going to use the idea of limits now to learn all about, they're called derivatives, basically how to find the slope of graphs at any point. We've already been introduced to the idea. We're going to take it and run with it.